Section 1 Introduction. We've been exploring how to make large language models, LLMs, generate text faster and more efficiently. Traditionally, these models create text one piece at a time, which can be slow and expensive. We found a promising approach called speculative sampling that speeds things up by breaking the process into two parts. First, guessing potential text pieces at a low cost, and then checking these guesses all at once. This method not only speeds up the process but also ensures the quality of the generated text remains high. To make speculative sampling work well, we need to start with a simpler version of the original LLM that can make quick drafts but is still similar enough to ensure quality. For example, in a series of models with different sizes, we might use a smaller model to draft text for a larger one. However, this isn't always straightforward, especially for the smallest models or those fine-tuned for specific tasks, because the differences in how they're trained can lead to inconsistencies. Some existing methods try to speed up the drafting phase by predicting text based on certain features of the LLM or using simpler prediction models. While these methods do make things faster, they often sacrifice accuracy. We've developed a new approach, called Eagle, that focuses on improving the drafting phase without losing accuracy. Instead of predicting the next piece of text directly, Eagle works by predicting certain features of the text, which helps avoid some of the uncertainties that can make drafting difficult. Our method has shown to be quite accurate and fast, making it a strong contender for speeding up LLMs. We tested Eagle against other speed-up methods and found it to be significantly faster, sometimes tripling the speed of text generation without compromising the quality. It's also compatible with other techniques that improve efficiency, meaning it could potentially make LLMs even faster and cheaper to run. Eagle is simple to implement, requiring just an additional component to the LLM, and it doesn't need any fine-tuning of the original model. This simplicity and reliability make it a versatile tool for speeding up a wide range of LLMs. We've successfully applied it to several models and scenarios, demonstrating its effectiveness and the potential for widespread use. In summary, Eagle represents a significant step forward in making LLMs faster and more efficient, offering a practical solution that maintains the quality of generated text while significantly reducing the time and cost involved. Section Summary. Auto-regressive decoding is the standard for large language models, but it's slow and costly. Speculative sampling divides the generation process into a draft stage, where potential tokens are guessed at low cost, and a verification stage, where these tokens are validated in parallel. Eagle, a new framework, performs auto-regressive operations at the feature level, achieving a draft accuracy of approximately 0.8 and offering a 3x acceleration for certain models, while maintaining the text distribution of the original language model. Section 2 Preliminaries. In our paper, we introduce some key terms and concepts that are essential for understanding our work. We refer to the large language model we aim to speed up as the target LLM, and the model we use for quickly creating initial drafts as the draft model. When we talk about a feature, we're usually referring to the data from the second to last layer of the LLM, which is a step before the final output layer, also known as the LM head. We use lowercase letters like T to represent individual tokens, E for their embeddings, F for features, and P for distributions. Sequences of these elements are represented by uppercase letters. For example, T_I, represents a sequence of tokens from the ITH to the JTH token. To explain how a large language model works, let's consider an input sequence of tokens. The model first converts these tokens into embeddings. These embeddings then go through several layers of the model to produce features. Finally, the LM head uses the last feature to predict a distribution for the next token, from which the actual next token is sampled. This process, known as vanilla auto-regression, can be simplified as a sequence of steps. Input tokens are turned into embeddings, which are processed to produce a feature, which is then used to predict the next token. We also discuss a technique called speculative sampling, which involves using a smaller model to quickly generate a draft sequence of tokens and their corresponding distributions. This draft is then checked by the target LLM in a verification phase, where tokens are either accepted or rejected based on their probabilities. This method allows us to maintain the quality of the generated text while speeding up the process. Moving on to our observations, we've found that working with features rather than tokens directly can be more efficient. This is because features, after being processed by the LM head, provide a more structured and predictable way to generate the next token. Our experiments have shown that auto-regressing at the feature level leads to higher accuracy and speed compared to working directly with tokens. Another important observation is the role of uncertainty in predicting the next feature. Since the target LLM generates text by predicting a distribution of possible next tokens, this introduces randomness into the process. When working with features, this randomness can lead to uncertainty about which feature should come next. To tackle this, we propose a method where the draft model takes into account the actual token that was chosen, reducing uncertainty and further increasing the efficiency of the process. In summary, our work focuses on improving the efficiency of large language models by introducing a draft model that works with features instead of tokens and addresses the uncertainty in feature prediction. Our experiments demonstrate significant improvements in both accuracy and speed, showing the potential of our approach. Section Summary. In this section, the authors introduce the notations and terminology used in the paper, including the distinction between the target LLM and the draft model, as well as the process of speculative sampling. The authors also present two key observations that motivate the design of Eagle. First, that auto-regressing features is easier than tokens, and second, that uncertainty in next feature predictions is important in text generation. They support these observations with experiments and illustrations, showing that auto-regressive feature processing followed by token generation yields higher accuracy and speedup compared to auto-regressive token processing, and that addressing uncertainty in feature predictions further increases the speedup ratio. Section 4 Eagle. We've developed a method called Eagle, which stands out because it includes both a drafting phase and a verification phase. This approach aligns with other methods that speculate on what might come next in a sequence but adds its own unique twists. In the drafting phase, the main thing that sets Eagle apart is how it predicts future elements. Unlike some methods that guess the next parts of a sequence independently, Eagle uses a combination of features and tokens from earlier in the sequence to make its predictions. For example, it can predict a new feature based on a sequence of previous features and tokens, then use this new feature to guess the next token. This process involves three main steps: embedding the tokens, using a part of the model called the LM head to work out the distribution for the next token, and then an auto-regression head that helps predict the next feature. The model cleverly combines these predictions to keep making guesses about what comes next, creating a draft that's structured like a tree. This tree structure is efficient because it allows us to draft a sequence of tokens in fewer steps than there are tokens. When it comes to training these draft models, we focus on two main tasks: predicting the next feature and predicting the next token. We use a type of error measurement called smooth L1 loss to get better at predicting features, and another measurement called cross-entropy loss to improve our token predictions. By combining these two, we can train our model effectively, even setting a specific weight to balance the two types of loss based on their importance. Interestingly, we found that Eagle doesn't need freshly generated text for training. It works just fine with a fixed dataset, which saves a lot of effort. We also add a bit of random noise to our training data to make the model more robust against small inaccuracies. In the verification phase, we use a technique called tree attention to quickly check the probabilities of each token in our draft. This step helps ensure that the sequence we've drafted is likely according to the original model we're trying to mimic. We adjust the tokens and their distributions as needed, using algorithms designed for speculative sampling. This way, we make sure our final output closely matches what the original model would have produced, setting us up nicely for the next round of drafting. In summary, Eagle is a sophisticated method that cleverly predicts the next parts of a sequence by building on what's come before. It trains efficiently, even on fixed datasets, and carefully checks its work to ensure high-quality results. Section Summary. The Eagle method consists of a drafting phase and a verification phase, with a focus on the drafting phase. Eagle's drafting model includes three modules: the embedding layer, LM head, and auto regression head, which work together to predict the next feature and sample the subsequent token. The training process involves using smooth L1 loss for predicting features and integrating regression loss and classification loss to optimize the auto regression head. Additionally, Eagle employs tree attention to compute the probability of each token in the tree structure draft during the verification phase, ensuring alignment with the original LLM's distribution. Section 5. Experiments. We carried out experiments on various models, including Vicuña models of sizes 7 billion, 13 billion, and 33 billion parameters, Llama 2 chat models of sizes 7 billion, 13 billion, and 70 billion parameters, and a Mixtral model with 8 times 7 billion parameters, known as Instruct v0.1. These sizes are typical for the large language models, LLMs, that are popular today. Our tests covered two main areas: dialogue and mathematical reasoning. For dialogue, we used MT-Bench, a set of realistic situational questions to see how well the models could handle multi-turn conversations and follow instructions. For math reasoning, we used the GSM-8K dataset, which is full of grade school math problems written by humans. In our experiments, we mostly used a batch size of 1, following the lead of other studies like Distill Spec and Build. This means we processed one example at a time, which is a method that has become quite common. When it comes to measuring our results, we focused more on how fast the models could run, latency, rather than how much they could do at once, throughput. We used three main metrics to see how well our method, Eagle, improved speed. The wall-time speedup ratio, which compares our method's speed to the original model. The average acceptance length, which is how many words the model can produce in one go. And the acceptance rate, which shows how accurate the model's first guesses are. For this last metric, we only looked at chain drafts because tree drafts can be tricky to measure with this method. Eagle was trained on the shared GPT platform, going through 68,000 dialogue iterations with a learning rate of 3E5. We used the Atom W optimizer with specific settings and limited the size of the updates to make sure the training went smoothly. Depending on the model size, Eagle added between 0.24 billion to 0.99 billion trainable parameters, with the Mixtral model having 0.28 billion. Training Eagle was quite efficient. For the largest models, it only took 1 to 2 days on a powerful server. In terms of effectiveness, Eagle showed impressive results. On certain models, it was 3 times faster than the original method, twice as fast as another method called Lookahead, and 1.6 times faster than Medusa. The speedup was especially noticeable in coding tasks, which rely a lot on fixed templates. Across different tasks, Eagle proved to be very effective, significantly increasing the number of words generated in one go compared to the original method. It also showed that it could handle errors in the input features quite well, maintaining good performance even when some errors were present. For the Mixtral model, Eagle managed to speed things up by 1.5 times. This wasn't as much as with some other models, partly because of a lower average acceptance length and the challenges of speeding up mixture of experts, MO, models with speculative sampling. MO models work by choosing the best experts for each word, and in the original method, only a couple of experts are needed for each word. But with speculative sampling, you might need to check more experts, which can slow things down compared to models that don't use this approach. Section Summary. The section describes experiments conducted on various large language models, LLMs, for dialogue and mathematical reasoning tasks, using speculative sampling with a batch size of 1. The metrics used for evaluation include wall-time speedup ratio, average acceptance length, and acceptance rate, with a focus on latency rather than throughput. Eagle, trained on the shared GPT platform, demonstrates notable effectiveness in accelerating LLMs, achieving speedups of 3x faster than vanilla auto-regressive decoding in certain models, and showcasing robustness to feature errors. Section 5.2 Case Study: Eagle plus GPT Fast. We explored how well Eagle works with other technologies designed to speed up processing. Specifically, we combined Eagle with GPT Fast, a tool that makes things run faster by simplifying data and compiling it more efficiently. Our tests showed that when we used Eagle and GPT Fast together, we could create text with Llama 2 Chat 7b on a single RTX 3090 graphics card at a speed of 160.4 tokens per second. This is a big jump from the 24.5 tokens per second we got using the standard methods provided by Hugging Face. In another part of our study, we looked at how Eagle uses a method called tree attention, which is a way of organizing data like a tree, for both creating and checking drafts. This is different from some other methods that line everything up in a chain. Our results showed that using tree attention lets us increase the length of text we accept by about 0.6 to 0.8 on average and makes the process about 0.3 to 0.5 times faster. Even though tree attention processes more data at once without needing more steps, the speed increase isn't as big as the increase in accepted text length. However, it's important to note that Eagle still significantly speeds up the process by about 2.2 to 2.7 times, even without using tree attention. We also experimented with what happens when we change what we feed into the draft models in Eagle. Unlike other methods, Eagle uses information calculated by the main language model and includes the outcomes of previous selections to deal with randomness. We tried 4 different types of inputs and found that using features, information calculated by the model, gives slightly better results than just using tokens, pieces of text, when the draft model is small. Combining features and tokens improves performance a bit because having exact tokens helps avoid mistakes that can build up when just using features. The best improvement comes from using features and tokens that are moved one step forward in time, which helps the model deal with randomness better. When it comes to training data, we found that Eagle works well even if we just use a fixed set of data for training. Generating new training data by making the target language model create responses to queries can make things a bit better, but it also makes training much more demanding. Our tests showed only a small improvement in performance, which suggests that sticking with a fixed dataset is a good strategy because it keeps training costs down. Lastly, we looked at how changing the number of tasks processed at once, batch size, affects how fast Eagle can generate text. Generally, as we try to do more things at once, the speedup we get from Eagle decreases. However, we found an interesting point where doing 4 tasks at once was actually faster than 3, because of how Eagle checks the text it generates. Despite focusing on reducing the time it takes to generate text, we also measured how much work Eagle can do in a given amount of time for different batch sizes. We found that Eagle can handle nearly the same amount of work as the standard method but can process twice as much information when we adjust the batch size to fit what our hardware can handle. Section Summary. The Eagle model is compatible with other acceleration technologies, as demonstrated by experiments combining Eagle with GPT Fast, resulting in a significant increase in generation speed. Eagle's use of tree attention and innovative inputs from the target LLM into the draft model, along with a fixed training dataset, contribute to its substantial acceleration effect and improved performance, especially in addressing randomness in the sampling process and reducing training costs. Additionally, Eagle's throughput is significantly increased, especially when operating under a memory constraint, making it advantageous for batch sizes exceeding 1. Section 6 Related Work. We've been diving deep into the world of making language models work faster. This involves clever tricks like distillation and quantization, all with the goal of speeding up how quickly a model can think through a problem. Our work shares some similarities with other projects that use what's called speculative sampling. This is a fancy way of saying we try to guess what the model is going to say next, but in a smart way that doesn't change the final outcome. In the early days, people focused on making the simplest form of guessing, greedy decoding, faster. But then, Speculative sampling came along and showed we could make even the more complex guessing methods faster without messing up what the model was originally going to say. This is tricky because keeping the model's original thoughts intact makes speeding things up harder. Some researchers have accepted that a little bit of change is okay if it means things can go faster. For example, DistillSpec tweaks how likely the model is to pick certain words based on a leniency function. Build lets some guesses pass if they're close enough to what the model would normally say, and Medusa uses a mix of strict rules and flexibility depending on how certain the model is about its guesses. Our method, Eagle, stands out because we don't compromise. We keep the model's original predictions exactly the same. The big differences between our approach and others mainly show up in the early stages of guessing. Speculative sampling, the technique we're all about, uses a simpler version of the big, complicated model to make these initial guesses. Some methods, like self-speculative decoding, skip parts of the big model to speed things up. Others, like spec-infer, use a bunch of smaller models to make a lot of guesses at once. There are also methods that layer these guesses in stages or train a special model just for making these guesses based on what it thinks will be asked. Interestingly, some approaches don't even use a separate model for making these early guesses. Instead, they pull tricks directly from the big model's playbook. And then there's REST, which looks back at past examples to come up with its guesses, and LLMA, which is super useful for things like fixing grammar, where it can often just tweak what's already there. So, in a nutshell, we're part of a big, innovative effort to make language models quicker on their feet, using a variety of clever techniques to guess what they're going to say next without losing the essence of their original thoughts.